Hello everyone, I'm Keerti and I'll be talking on improved distance oracles and a distance sensitivity oracle with subquadratic space. This is a joint work with Davide, Shiri, Sarel, Tobias and Martin. Okay, so first we'll see what is a fault tolerant model. In a fault tolerant model, we are given a graph G with vertices and edges. The edges can have weights associated with them, and this network is prone to failures. So at any instant of time, there can be some edges failing in the network. Also, there is a bound on maximum number of edges that can fail at any instance. For example, in this graph, at most 2 edges can fail. Now, as these failures are occurring in the graph, we can be interested in querying certain properties of the graph. So in this talk, we'll be looking at the problem of answering distance queries, and we'll be considering the static setting as well as fault tolerant setting. Okay, and let us first see what is the goal in the static scenario. What we are interested in is computing approximate distance oracle, which is a compact data structure typically of size much smaller than n square, and is the number of vertices in the graph. And given any query vertex pairs, say x and y, the oracle should be able to report approximate distance between x and y in the graph G. Now the goals here are that the space taken by this data structure should be very small. The time to report this approximate distance should also be small, and the stretch of the oracle should not be too large. So we say that stretch of the oracle is alpha comma beta if for any x comma y the reported distance is as large as the original distance, but it's bounded by alpha times original distance plus an additive error beta. Similar to distance oracle, we can define distance sensitivity oracle with a parameter f. So here as an input we'll get a triplet consisting of 2 vertices x and y and a failing set f. The cardinality of f is bounded by small f. Now the oracle should output approximate distance between x and y in the graph G minus f. The goals remain same. Size of the oracle should be small. Time to report this approximate distance should also be small, and the stretch alpha beta should not be too large. Okay, it's natural to ask why we are considering approximation and not exact distance problem. So it's very easy to construct bad graphs which are just dense bipartite graphs for which any distance oracle which is able to report distances of stretch alpha beta satisfying alpha plus beta is 3 or more must take omega n square size. And that's why if you are interested in having a compact oracle whose size is much smaller than n square, then the only possibility is having oracles with some additive or multiplicative stretch. Okay, we'll now see our results for static distance oracles and what were the prior work in this setting. Thorup and Zwick in 2001 in their work on distance oracles showed that for any integer k we can compute a distance oracle of stretch 2k minus 1, additive error 0, and the oracle is taking a space which is just k into n to power 1 plus 1 over k, and given any query pair x and y, it can report the 2k minus 1 stretch distance in just order k time. Later it was the order k term was also improved to order 1. So after this, a natural question was, can we bring down the stretch below 3? So Petrasco and Rodati showed that it's possible to obtain an oracle of stretch 2, 1, query time constant, and space was n to power 5 by 3. Also, Agarwal and Godfrey considered the question of computing oracles for sparse graphs. So they showed that for any constant c, you can have an oracle which has m plus n to power 2 minus c space. This will be subquadratic in n if graph is sparse. The stretch of the oracle can be made arbitrarily small, so the stretch was 1 plus epsilon comma 0, and their query time was a function of average degree and of course parameters c and epsilon. So the query time was n to power c into average degree whole to power 1 by epsilon. Now it's natural to ask if we can get oracles which have nice space which is subquadratic in n, query time which is sublinear in n, and stretch is also close to 1 plus epsilon. So we show that it's indeed possible. So this is the open problem that we study, and we show that it's possible to obtain an oracle which has multiplicative stretch 1 plus epsilon, additive error is 2, the query time is n to power c, and the space is n to power 2 minus epsilon c. The only constraints on epsilon and c is that their product should be bounded by half and epsilon inverse should be an integer. So here we can make query time arbitrarily small, stretch also arbitrarily small. Of course, the sum total stretch, the multiplicative stretch and additive stretch cannot go below 3, and space of our oracle will be function of the epsilon and c that we choose. Let us see an overview of our static oracle. So our oracle construction is very easy. It just stores two things. First is for each of the vertices v1 to vn, it stores a partial BFS tree with the closest L vertices. Next, it computes a hitting set for these partial BFS trees. So the size of the hitting set will be n over L into log n. And if for the hitting set R, it also stores the R cross V distance matrix. So the total space is n into L to store the partial BFS trees, and to store this R cross V distance matrix, the space taken is n into n by L log n. Okay, so we next define the notion of short and long BFS. So for any xy shortest path P of length d, we define this short and long BFS notion for only the vertices lying on the shortest path. So for a vertex V on the path P, if the height of the partial BFS tree of V is bounded by 1 plus epsilon d, so epsilon is the parameter, stretch parameter that we choose, and d is the length of the shortest path. So if the height is bounded by 1 plus epsilon d, then we say that V has a short partial BFS tree, and if it's more than 1 plus epsilon d, then we say that it's, the partial BFS tree is long. Okay, now our algorithm is divided into two cases depending upon whether the vertices on the shortest path have short BFS or long BFS. So case 1 is P contains a vertex V which is a short BFS, which has a short BFS. So suppose this is a shortest path between x and y, and there's a vertex V whose partial BFS tree has a height at most 1 plus epsilon d. Then note that using triangle inequality, we can show that x to r distance plus r to y distance is at most the original distance d plus twice of this length 1 plus epsilon, twice of 1 plus epsilon d for any vertex r in this partial BFS tree. Now since the partial BFS tree will have a non-empty intersection with the random set, what we can do is we can look at all the vertices in the random set and um, look at the value which is x to r distance and r to y distance. And if we take the minimum one, then at least one vertex we'll get from this partial BFS tree. And for the resultant path, the stretch will be at most d plus twice of this term, which was 1 plus epsilon d, and this will turn out to be d into 1 plus 2 epsilon and an additive value of 2. So the stretch will be 1 plus 2 epsilon comma 2. Now since we have stored the partial distance matrix, the time to report distance in this scenario is just coordinate of r, which is n by l log n. So this is case 1. The complementary case will be when the shortest path has no vertex which has a short partial BFS. So suppose all vertices on the shortest path have long partial BFS. Then observe that if we take any vertex v on the shortest path, and if we traverse the vertices in its partial BFS, then we'll be able to travel at least epsilon d distance along the path. So using this observation, we get a natural algorithm for tracing this x to y path, and what we do is just recursively explore the partial BFS tree starting from x up to just 1 plus epsilon depth. So since each partial BFS will be able to traverse a length of at least epsilon d, and the number of hops we'll need is just 1 plus epsilon. And while storing the partial BFS tree, we could also store the distances, so the time to do this traversal will be just L to power 1 by epsilon. We also show that it's possible to bring down this time complexity to L to power 1 by 2 epsilon, and the argument is instead of doing a single traversal from x to y, we can start a traversal from x as well as y simultaneously, and we'll just go up to 1 over 2 epsilon depth, and somewhere we'll meet in between, so the time complexity can be reduced. Now our algorithm just takes the best of case 1 and case 2. So for any n vertex graph with parameter L, we are able to obtain a oracle whose stretch is 1 plus 2 epsilon comma 2. Query time is n by L into log n plus an additive term of L to power 1 by 2 epsilon, and space is nl plus n square by L into log n. So this was an overview of our static oracle construction, and now we'll move to sensitivity oracle. Okay, so for this problem of computing distance oracle for fault-tolerant graphs, Chechik et al. Were first one to obtain an oracle which took subquadratic space. They showed that for any integer k and for any parameter f, we are able to obtain an oracle which has stretch 8k minus 2 into f plus 1, query time of order f, and space is f into k into n to power 1 plus 1 over k. So here query time is close to optimal. Space also is very efficient as it's close to Torubzvik or space bound, and stretch we get is quite large. Even for k equals to 2, the stretch will be 14 into f plus 1. So after this, a natural question was, can we bring down this stretch? And recently, last year, Bilò et al. Showed that it's indeed possible to obtain an oracle which has stretch 3 plus epsilon comma 0. The query time was not constant, but it's sublinear in n, and the space is subquadratic in n. um, Now, we asked the question, can we bring the stretch further below 3? And we showed that it's possible. So, for parameters c, any constant c, integer t, and sensitivity f, we show that it's possible to obtain a FDSO whose stretch is 1 plus 1 over t into 1 plus epsilon comma 2. Query time is n to power c, and space is subquadratic in n. And the constraints on c and t is c should be bounded by t plus 1 over 2. So we are able to bring down the stretch arbitrarily close to 1 because we can make t large and epsilon small. Query time can be made also extremely small because you can make c small, and the space will be the function of c, t, and f, also the epsilon that we choose. Now to obtain this DSO, we give two black box reductions. First reduction is from static distance oracle to distance sensitivity oracle for replacement paths of bounded length. So this oracle, this bounded length DSO is able to give good answers for all shortest paths whose length is bounded by some parameter L. And if the length is not bounded by parameter L in the surviving graph, then a stretch can be too large. So if the distance oracle has stretch alpha beta, query time q, and space s, then our FDSO has stretch alpha comma beta same. Query time is increased by an additive term of L, and space gets increased by a multiplicative factor of L to power f, ignoring log and f factors. Our second black box reduction converts this bounded length FDSO to general FDSO. So the constraint we have on the parameter L is that it should be bounded by n to power 1 over 2f, and we show that if we have a bounded length FDSO with stretch alpha beta, query time q, and space s, then we can get oracle which has stretch alpha into 1 plus epsilon comma beta. So additive error remains same, multiplicative error is increased by just 1 plus epsilon factor. The query time is increased by a factor of L to power f minus 1, and space is increased by a factor of n square by L, ignoring log terms. So these are two black box reductions that help us to obtain DSOs which have a very small stretch, very small query time, but a higher space bound which is still subquadratic in n. Coming to open problems, so there are two main open problems that we think would be interesting to solve. First is can we get distance oracle or distance sensitivity oracle which has purely additive stretch, and query time is still sublinear in n, and space is subquadratic in n. Second major open problem is can we obtain a constant query time? So till date there is no DO or DSO with stretch smaller than 2 which has constant query time. So it will be interesting to obtain a stretch of 1 plus epsilon comma order 1, query time order 1, and space which is subquadratic in n. So that's all. Thank you.